Good morning, sir. This is Jashan Jindal along with Ayush and Siddhi Ojha, and today we will be presenting our Tier 3 topic, which will be extending functionalities in the 8051 microcontroller. Table of contents are introduction, objective, working principles and methodology, work completed with results, conclusion and references. So what is the 8051 microcontroller? Let's see. 8051 microcontroller is an 8-bit microcontroller developed, manufactured and marketed by Intel Corporation. The purpose of this project is that after learning through the semester deeply about the 8051 microcontroller design specification, IC interfacing capabilities, is to apply this knowledge and further explore on how certain additional functionalities can be implemented. We divide our discussion basically into research. We divide our discussion and research into mainly three parts: interfacing utilities, mathematical utilities, and simple encryption. First is interfacing utilities, that is creating long delays and generating standard baud rates, providing an interface to provide this functionality with fewer inputs and ease. You will see code plus theory. And mathematical utilities like implementing a 8-bit floating point and the concept on how we can get standard trigonometric function values. We will see that. And third is simple encryption algorithm to protect and hide data. We will see code plus theory. So the objective of this project is the purpose of this project is that after learning through the semester deeply about the 18 microcontrollers design specifications, is to apply this solution. So next my teammate Ayush will be taking over this.
Hello, sir. My name is Ayush, and I'll be talking about the working principle of the libraries that we made. So, most of the coding that we have done for the library is based on the things that we were taught this semester and a little bit of research. So, the first thing is the interfacing library. So, the interfacing library mainly has two parts, right? The baud set and the long delay generation. The main idea behind this library is to give as minimum input uh, from the user side to generate long delays and set the baud rate. So the two things that we have here, the way I've implemented this is this I'll jump to baud rate or timers. I'll talk about the timer first. So I was going to implement it in mode 2. So if you wanted to make uh, if you want to generate a delay less than 71 milliseconds, you could have done so in mode 2. But for now I've used mode 1 only, and I'll be showing you mode 1. So for example, the way we actually create delays, the user just has to put values in R0 and R4. He has to put these values in such a way that when you multiply the values in R0 R4, that's the total value of delay that you want. So here we have 80 into 3, 240 milliseconds delay. So the idea behind using two registers is mainly that so I can extend the total number of the total value that we can actually create a delay of. So using two registers, I can create a delay of approximately 1 minute. So the idea is pretty simple. We divide by 71 uh, this number, the R0 by 71, and then R4 stands as your outer loop, right? But we do have one problem. So say if you're dividing 140 by 71, right? Since it's an integer division, 140 by 71 will give 1, even though it's much more closer to 2. So to offset when we get such values, what I thought of was to create a breakpoint at or a benchmark at like half more of 71 when you add it to it. So 71 plus 35, 106. Right. So you increment R2 once again. So R2 is basically going to hold how many times we need to run our inner loop, right? So we check if it's more than 1060. Probably a better way to do would be to actually analyze at what exact value do the division by 71 actually gets much more closer to 2. But for sake of simplicity, I've used 106, right? So we calculate, we divide, we have the loop over here to calculate the total number of times we need to run our roll over our timer, and then we implement our timer delay over here. So this nested loop implies the existence of both those numbers, uses both those numbers R2 R4 to create that delay, and to show that the delay that we're creating is correct, right? So I've used port 2.3, basically we'll see a sharp rise or change in the bit state when this delay is over. So if I am to run this, right, so I'll jump to timer because we're talking about timer. Mode 1, we create the delays. Since it's not more than 106, we're straight up just gonna go to the calculation and not add add the offset. So yeah, there we go. So we see the sharp rise after 0.21 seconds, right? This is about 240 milliseconds. Of course, there's going to be a little bit of a difference, not exact 240 seconds, because we are using integer division, and a lot of significance is lost while doing so. Maybe if we had chosen a much more mathematically astute number, this number can still be brought closer to 240. So the second thing that we have here is the baud rate generation, right? So the idea behind the baud rate generation is also pretty simple. Uh, you basically have a few common um, baud rates that you want to operate at. So you simply store the values that you need to keep in th1 in a lookup table inside the code memory. So using the data pointer, we get the, so if it's mode 0, it will map to this one over here, mode 1, mode 2, mode 3, mode 4. Obviously mode 3, mode 4 are the same one, except in mode 4 you also need to turn on smod, right, to double the baud rate. So that's what I did over here. So we need one conditional to check. If we do get 4, then, and so we'd have to double it, right? And since pcon is not bit addressable, we'll have to set the bit in accumulator and then move it to pcon. So I've written a basic transmission function, transmit the data, right? uh, Using the same kind of thing that we use in class. Basically whenever we give this symbol, it means the transmission has ended. So if I go ahead and save this and run this, we don't need this window anymore. Mainly we need the UART, right? There we go. So mainly the baud rate. If I go ahead and right, there we go, we have transmitted the data that we wanted. So over here I chose 19,200, but we can choose any number, and we just have to put it in R0, and that's the baud rate we're going to run it. Now the second thing that we wanted to talk about is the mathematical utilities, right? So a lot of different tools we might require to express our problem or whatever issue we're trying to solve, right? So one of them, as we saw, that lack of floating point, right? The lack of floating point. So even floating points can be implemented in 8 bits, but 8 bits isn't a lot, so you can't really represent too much, right? We have a system of mini floats. So the mini floats are good for representing floating point values, especially if you don't want too much change, right, in the values of the floating point. So we can represent them. For example, we have over here, right, this 8 bit is going to represent 2.75. So basically you define a representation. Over here we have a 7 bit axis, right? Over here we have a 3 bit axis, so we have to subtract the axis from the exponent, and then the mantissa into the exponent, then we standardize this, and then you based on the values add them up and you get your value. uh, the second thing that I want to talk about was the implementing functions, right? We might require values of sin x and cos x, so how can we do it? So there's one way that you can do it is using Taylor series. So basically what you do is you take a few terms out of these. So for cos x, right, so I want to find cos of something. So you take the first three terms, you just put in the values and do the simple operations. So as many of these terms you're going to take, the more precise your value is going to be. Same thing you can do for sine x, e to the power x, and any functions that you can write a Taylor series for. Now obviously we can't write a Taylor series for all functions. This one, and the second thing is this isn't going to be very precise, right, for integer division as we saw in the previous one. So the better option, right, and this is the option that they have, even C designers have used while implementing their mat.h library, mainly because they had to cater to a lot of different machines, right? So they can't assume that a certain machine can run floating point operations pretty well. So the better option to go for is an lookup table. So you basically store the values, and as many values you have in that lookup table, the more precise you can find out the values for cos x and sin x. Now, the third and the last thing was data protection and 8051 encryption, right? So, data protection and 8051 encryption. So, 8 bits, like I talked before, isn't that much, right? If you were going to generate all the possible keys for 8 bit, that's only like 256, very easily brute forceable. So, in general, people and as a standard use 128 bit. 256 bit is also used to it's referred to be military grade. 256 bit is referred to be a military grade encryption, but 128 is usually sufficient. So 128 bits, because apparently to try to enumerate all possible keys for 128 bits, it's going to take 5 times more than the size of the universe, right? So 128 bit is at the moment pretty secure. So for this one, mainly we have implemented the XOR cipher, right? Uh, the XOR cipher basically is that if you have some text, right, and you have your key over here, you XOR them, you get an encrypted text, and if you XOR it with that key again, you get whatever your data value was before. So this is also used in the standard for the encryption algorithm, the AES, right? AES also has two types different, right? AES 128 bit, AES 256 bit, the military grade one. So even it utilizes the XOR cipher during one of its round, but obviously it's a little more. It has a little bit more steps, right? It has dividing of data into different blocks. So other than that, that's what we have implemented over here using this XOR cipher. That's what I'm going to show. Yeah, so we have the encryption and decryption. I'll go ahead and first show you the encryption. Right. So the values that we're going to be encrypting, right, are over here. This is the key that we're using. We're going to actually also divide our data into blocks. So these are 16 locations, 128 bit, and your key that's going to work on them is also 128 bit, right? So basically we're going to have a D pointer that's going to XOR these and then store the value in 10h location, memory location, as we'll see over here. That's 16 for the 16 memory locations that we have to do it each time for, and that's offset keys is to get the next one, right, the next value by increasing the D pointer. So if I go ahead and just right, let's assemble this first. We're going to be looking at 10h, right? That's where our values is going to be showing up for the encryption. I think I messed up. Yeah, this needs to be here.
So, as my teammate have discussed some functions in 8051 in detail, so I'm just concluding some functions that we have discussed in this project. First one function it is interfacing utilities. We have created the long delays and generating standard baud rates. We have provided an interface to provide this functionality with fewer inputs. Second function we have discussed in this project is mathematical utilities. We have implement how to means we have shown that how to implement the 8-bit floating point and the concept on how we can get the standard trigonometric function values. Then third function we have discussed is simple encryption algorithm to that how to protect and hide the data. These are some extended functions we have explored in 8051. These functions can be used to increase the range of the application or have the greater reach and versatility. So this is our project. We have done it, and I hope that through this project we can have the more exploration in 8051. These are some references we have taken a help from it. So to make this project, and thank you from behalf of my team to all of you. Thank you.